Hello everyone, this is Kevin Cofield with Cofield Aviation. Welcome to this YouTube video of operation of systems. I appreciate you taking the time to invest in your personal education, um, uh, good aeronautical decision making, and risk management. So, uh, operation of systems, where that kind of falls into that PAVE checklist when we're talking about aeronautical decision making and risk management. P stands for pilot, A stands for airplane, V stands for environment, E stands for external pressure. So operation of systems falls in that the aircraft, the A of the PAVE checklist, along with airworthiness requirements and performance limitations. This video is going to be centered around the Cessna 172, more specifically the Cessna 172 Mike model, which is a carbureted engine. Some of the newer 172s have fuel-injected engines, but operation systems is, in this video will focus on the 172 Mike model. Now, operation of systems is going to be aircraft specific. So if you're flying an Archer or any other aircraft, make sure you reference the POH. Remember, the Bible for the airplane is basically the airplane's flight manual / POH, according to what is required via the type certificate data sheet. But for the Cofield Aviation students, the Cessna 172 Mike is what they're flying. So that's what we're going to focus in on this video. So let's go ahead and get started and talk about the operation of systems and all the systems that are associated with the 172 Mike. So the way I kind of like to start this is I'm actually going to go here to we're here on the website cofieldaviation.com. Going to go to the student section, going to go to downloads, and then we're going to pick here the operation of systems. And this is a printable PDF file, so you can print this off, use it for your reference. Again, it's just for the 172 Mike model. However, there are other items like, when we talk about electrical system, are all usually about the same on most small GA airplanes. Pitot-static instruments are about the same, so can be still useful information even if you're not flying a 172 Mike model. But what we're going to start out with is we're going to start out with the power plant. So this is all coming straight out of the ACS, the Airmen Certification Standards. So if you don't have a copy of the ACS, you really need to, because that's basically what your entire check ride is based upon, is the private pilot ACS. So this is the operation of systems, is the pre-flight preparation items of the ACS, which is basically going to be part of your oral exam. But I always say, when we go to a new airplane, we need to be a master of that airplane. So operation of systems, the POH, the AFM, this is how we become a master of the airplane. We don't need to build the airplane. We don't need to be engineers. We just need to know enough about the systems so that we can work an issue in the cockpit when we have system malfunctions and all, that we can work it out to where we can get it on the ground and then leave it to the mechanic from there. We don't have to be mechanics or engineers, but we just need to know enough about the airplane to safely work the problem, get it on the ground, and let it be somebody else's problem. But we're going to start off with again, the 172 Mike model that we fly. The power plant is a Lycoming 0320 E2D engine. If you remember us talking in airworthiness requirements, we looked up the type certificate data sheet, and that explains exactly what engine we have in the airplane, limitations, weight limitations, fuel limitations, center of gravity, and all that. It's a great treasure trove of information. We'll look at that at the end of this for the 172 Mike model. But basically, this can come out of the type certificate data sheet from the FAA's website, and then of course your AFM, your flight manual, right out of that. So we have the Lycoming 0320 E2D engine. So this O means it's horizontally opposed. If you have a fuel injected engine, you're going to have an I. So it would be like an IO 320, IO, whatever. So the I would stand for injected. This engine is not fuel injected, so we have a carbureted engine, which we'll talk about more in depth in just a minute. But our engine, we have a Ram conversion, making it 160 horsepower. If you look at the type certificate data sheet for the 172 Mike, you're going to see the Lycoming 0320 E2D engine, but you're going to see it's rated at a maximum RPM of 2,700 RPM and a maximum RPM of maximum horsepower of 150 horsepower. So ours is not that. So that means if we've made a change to the type certificate data sheet, then that means we have to have a supplement to the type certificate. So we need an STC. So we have an STC that makes our engine 160 horsepower here. So we'll look at that STC on the next slide here in just a minute. But for our 172 Mike model, November 61651, 160 horsepower is your RPM. And then we're going to get into, so it's 2,700 RPM max and 160 horsepower. That's only for 5 minutes. Let me just go ahead and show you where I'm getting this information. So here is our Ram STC over here in the corner. And this is basically looks just kind of like a type certificate data sheet, right? So we have the engine. There's our engine. We have the 0320 E2D. Minimum fuel now is 100 octane. That's different than the type certificate data sheet, which says it's 80 minimum. This bumps it up to 100 minimum octane. The propeller here are the only propellers that we can use since we're not a seaplane. And then engine limits down here. So this is the important part. So our engine limit is we have a max continuous of 150 horsepower and 2,650 RPM. So that's max continuous, no limit on how long you can fly it at 2,650 RPMs. However, for takeoff, we have a 5-minute limitation of 160 horsepower. So there's that 160 horsepower we get, but that's only for 5 minutes, maximum RPM of 2,700 RPM. So it's important to know your limitations of your personal airplane, right? So normally you can go the type certificate data sheet or your AFM, but because we have an STC, we have to go to our STC to get those limitations. So for our airplane, it is 160 horsepower, 2,700 RPM, max for 5 minutes, and then 150 horsepower, 2,650 RPM, max continuous there. There's some of your, basically your limitations: oil pressure, cylinder head temperature limitations, maximum of 500. Green arc, 225 to 425, that's important. We have an engine monitor in our 172. We want to make sure our cylinder head temps do not really get above, about 430 or so in the climb. That's when we're going to start doing something about it pretty much right now, which, we're going to talk, this is an air-cooled engine. So the only way we can cool it down is to get more airflow and or also reduce power. So that's why in the checklist, we kind of bring the power back a little bit, accelerate to VY plus 10, and to increase engine cooling. And we have an engine monitor that shows us our cylinder head temperatures, and we just keep those well below, 420 is really where you kind of want to be, that or lower. But sometimes you'll see it get to, 430 or so, and especially in the summertime. So we just start doing something about it, so we don't get anywhere close to that 500 red line. I would say 440 would be kind of the max that you want there. But let's go back here to the slide. So we talked about the maximum RPM, 2,700 RPM, 160 horsepower. That's for 5 minutes. And then 2,650 RPM, 150 horsepower max continuous. Now, when you're going to get this, we kind of have to talk a little bit about performance and limitations as well in operation of systems, because you're not always going to get 160 horsepower for that 5 minutes or 150 horsepower max continuous in all conditions. Okay, we're only going to get that at sea level and standard temperature. Okay, so sea level pressure, 299 or 2. Again, this is going to be performance and limitations, so it's okay if you don't understand all that right now. You'll learn that in performance and limitations. But sea level 299 or 2, and then standard temperature, which is 15 degrees Celsius at sea level. So you're only going to get 160 horsepower then. When it's warmer than that, you're not going to get 160 horsepower, okay? Several things are affected in the engine because we are normally aspirated. So we have 4 cylinders, so it's a 4-cylinder engine, and it is a normally aspirated engine, which means it's breathing the air that is breathing outside. Okay, we don't have a turbocharger to increase the air pressure. So again, this is kind of performance limitations, but as we go up higher in the atmosphere, the air gets thinner and thinner and thinner. So that thinner air, that less pressure, it's about 1 inch per 1,000 feet of less pressure. So that lesser pressure then affects the engine performance and the fact that your engine performance goes down. Okay, so as we go up higher in the altitude, we're not making 160 horsepower anymore. That power is degrading because it's normally aspirated. Now, if you fly an aircraft that has a turbocharger will actually boost the air pressure. So like on the ground, 299 at sea level. So that's basically, say, about 30 inches, close to 30 inches of pressure. A turbocharger can, for a Cirrus SR22T, which is the turbocharge, it has a manifold pressure of 36, I believe, 36 inches. So it increases that pressure by 6 inches from sea level. So it's almost like the airplane thinks it's about minus 6,000 feet below sea level, which is a lot better pressure, which means that's a lot better performance. And a turbocharger is going to keep that same amount of power all the way up. In the case of a Cirrus, it keeps that 36 inches all the way up to 18,000 feet, which is pretty incredible, right? So in a turbocharged airplane, you keep this power all the way up because your engine is turbocharged, not normally aspirated. But our airplane is normally aspirated, meaning it's breathing the air that is breathing outside. There's nothing to help increase that airflow to help increase that pressure. So as we go up in altitude, we're not making 160 horsepower. Okay, it gets less and less and less, and that's what you'll see in the performance charts in performance limitations. When we do those calculations, you'll understand that. Air-cooled, we already talked about that. It's an air-cooled and oil-cooled engine. The oil circulates to help for the lubrication of the engine there. So the big one here is air-cooled. We talked about the maximum cylinder head temperature, red line of 500. We never even want to get close to that. 440 should kind of be the absolute red line, to where we're aggressively doing something to keep it in that green arc, where the green arc, if you saw in the SEC, stopped at 425. So we really want to keep it, in that green arc below 425. So how do we do that? It's air cooled. So we have to increase the airspeed to help with the cooling. And then if it's just not enough to increase the airspeed, we can also reduce power, which would reduce the amount of heat and friction inside that engine. Also, oil, of course, helps with that as well. And when we talk about mixture and stuff here just a little bit, that can help as well if you're running rich at peak or so forth. So air cooled, oil cooled engine. Really big thing here is just keeping that cylinder head temperature down. Really, I think it's important to have engine monitors in these airplanes. We only have one engine, so there's no redundancy in that. So let's know exactly what's going on with that engine at all times. So we have 4 cylinders, so we know the cylinder head temp for all 4. We know the exhaust gas temperatures for all 4. And the most important of that, EGT really doesn't matter. Okay, the most important of that is cylinder head temperature. Really, cylinder head pressure is what's most important, but we don't have the ability to see cylinder head pressure. So the closest correlation to cylinder head pressure is cylinder head temperature. So if you keep those cylinder head temperatures well below 420 at all times, you're going to get much more longevity out of that engine. So do that by increasing airspeed, reducing power if you need to. So the way I like to start breaking down these systems is by what makes this engine run. Okay, I just talked about we only have one engine, right? So we have redundancies built in to this fuel, fire, and air. That's what makes an engine run, is fuel, fire, and air right there, okay? So we build in redundancy to the fuel, we build in redundancy to the fire, and we build in redundancy to the air because we only have one engine. So we want to back up if we have, one fire system or one air or one goes out, then the other one will pick up and the engine will not quit. Okay, so pre-flight takeoff, the run up, we're checking redundancy. We check the redundancy in the fuel, fire, and air. Now this goes for any engine. Okay, it just may be different of how you get the air to your engine or the fuel to your engine. Like if you have low wings and pipers, you're going to have fuel pumps and all of that with the fuel. So you're checking that redundancy and so forth. If you've got a fuel-injected engine, your air is going to be a little bit different than a carbureted engine. You might have an alternate air source, or it might be automatic, like a newer 182. But what really matters here is in the power plant, what makes that engine run? Fuel, fire, and air makes that run. So let's talk about the redundancies that are built into that. So we're just going to go through each one of these and talk in detail. So let's first talk about the fuel system. All right, we're going to talk about the fuel system. We're going to go down here until we get to the fuel, and there it is right there. All right, so we have a maximum capacity of 42 gallons. Again, this can be found on the type certificate data sheet. I'll show that at the end of the video. But we don't really care about max capacity. What we care about is the gallons usable. Okay, so 38 gallons usable is what we have access for flight planning and actual usable fuel. So all we care about is that. The other 4 gallons is fuel that we don't have access to. So whether it's fuel that's in the lines or whatever, we just do not have access. We don't have to know why. We don't have to whatever. We just do not have access to that fuel. So all we care about is not the 42, but the 38 gallons usable. So that's 19 gallons usable per side. So how we get fuel from the tanks down here to the engine is pretty simple. In the 172 mic model, pretty much all the 172s, it is all gravity, okay? So these fuel tanks are sitting inside the wings, and the engine is sitting down here below the wings. So it's pretty easy that the fuel will just flow with gravity. I don't think gravity is going away anytime soon, right? Now, obviously, we're not going to fly the airplane upside down, because then we would stop the fuel flow to the engine would quit, right? We're not doing that in 172s. We're keeping it straight and level. That's how we get the fuel from the tanks to the engine. Now, again, gravity is not going anywhere. So why do we need redundancy in gravity? It's not that we need redundancy in gravity. We talked about we have redundancy built into all 3 of those things that makes the engine run: fuel, fire, and air. So what's our redundancy with the fuel? Gravity doesn't work great unless we vent it properly. So the way I kind of like to explain this, way back in the old days when I grew up, gas cans had a little thing on the back of it that you would pop up, and it would allow the fuel to flow very evenly, right? So when you're putting it on the lawnmower, you pop that little vent on the back of the gas can, and it would just flow really nicely. All right, that's what we're doing right here, is we're just venting it and making it flow real nice. I think the EPA probably had some issue with that, because I think it would spill fuel out of the back, right? So the EPA got rid of those, and now when you do it, we don't have that little vent back there. Now it's like clunk, 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 right? It doesn't flow very well. So that's a direct indication of why we need redundancy built into the vent system for a gravity-fed system, all right? So how do we do that? All right, so we got 2 ways we can vent to keep this fuel flowing steadily, okay? So the first primary way is right here. So it's the fuel expansion vent tube, all right? So this is located on the left wing. You'll look at it at pre-flight. You want to make sure that it is clear, because that is our primary way to vent it. And if you look right here, That fuel expansion vent tube vents both tanks because we have this interconnect right here, okay? So this one vent vents both tanks, all right? So problem solved, right? That will keep the fuel flowing nicely, all right? But I said we need redundancy, right? So we're not going to rely on just that. So let's just say this got blocked. So whether, uh, you hit a bird or, for whatever reason, this bug or whatever, this vent gets blocked, okay? If we did not have an alternate way to vent it, then the fuel would not flow correctly and the engine would quit because it would be starved of fuel. If you starve it of any of those three items, fuel, fire, air, it's going to quit, right? So our redundancy is right here. So we have these vented filler caps. We have it right here on the left tank, and then we have a vented filler cap here on the right tank. If you look in this diagram, you see where it says vented filler cap here, and then it just says filler cap here. So why did I say this is vented if it doesn't say it is vented? Well, back in, I think it was probably the 80s, an AD come out. So remember airworthiness directives, talk about AD. Also, this airplane doesn't require an AFM, so it's not updated. So this is just the old POH. But an AD came out and said that we had to replace this. And that's pretty smart because this is our redundancy, right? So an AD came out like in the 80s that you had to replace this with a vented filler cap. So now each cap is vented. So that's our redundancy. That's how we can keep the fuel flowing down to the engine. So it's not that we have to have redundancy for gravity. It's the fact that because it's gravity, we have to have it vented properly so that it can flow. If you fly in a low-wing airplane, your redundancy is fuel pumps. You have an engine-driven fuel pump, and then you have electric fuel pumps that will pick up in the event that the engine-driven fuel pump fails. So whatever system you have redundancy built into it, okay? So our redundancy is, again, the filler caps, okay? So the fuel flows out of the tanks and then to this fuel selector right here. So the fuel selector, the way it's sitting right here is on both, so that means it's taking fuel out of both tanks. That's where you're going to run this thing 99.9% of the time, okay? If you made the selector like this, pointing to the right, that means it shuts the fuel off to the left tank and you're only running on the right tank, all right? If you then conversely put that fuel selector to the left, that means that you're running on just the left tank and you're shutting off the right tank. And then this also has an off function where it stops the flow totally. You would only use that in like an engine fire, scenario, but we've got to have the ability to shut off fuel so it doesn't, feed a fire or whatever. Other than that, it's a very simple system. So you're always going to have this in both. The fuel is going to flow down here to a fuel strainer. So this is the lowest point in the fuel system. This is what you're pulling underneath the cowling when you're draining, going down there and sticking the sump down in there and draining fuel into it. So you're checking for water, contaminants, anything like that, because this is the lowest point in the fuel system. So it's kind of basically like your little fuel filter, if you will, this fuel strainer here. Okay, what we can tap off of that is an engine primer. So we have an engine primer. It's only used for engine starts when it's really nice and cold. Otherwise, this is always locked in position, but it bypasses the carburetor mixture control and all of that and goes straight and dumps fuel directly into the cylinder only for engine start. You would not want to use this at all in flight because guess what? If you did, you're bypassing the carburetor where you get the correct fuel air mixture, which makes the engine run nice and smooth. You could flood the engine by doing this, and then obviously if you flood the engine would quit, okay? So it's kind of like a choke, but engine primer only used for starting. And then simply, this fuel comes down here to the carburetor. Inside the carburetor is where we get the correct fuel-air ratio for that engine. And how do we control that? So if you look at these two controls in the carburetor, we have a throttle and we have a throttle here, and then we have a mixture control. So why do we have a mixture control? So this is a little red knob in the airplane. What it does is it controls the fuel air mixture inside of this carburetor. Okay, so we're going to talk a little bit about performance again. When we go up in the atmosphere, what's happening to the air, right? It's getting thinner. So in order to have the correct fuel air ratio, look at your POH and go by what the POH is telling you. But in our POH, it says above 3,000 feet, and this would be density altitude. So again, if you don't understand these terms, that's fine. That's in performance and limitations. You will learn it there. But above 3,000 feet density altitude is when you would start to lean using this mixture, the fuel. And what do I mean by that? So as we go up in the atmosphere, the air gets thinner. Okay, so what we have to do is we have to take fuel as the air gets thinner and thinner and thinner. We have to take fuel away from it to correct the correct fuel air ratio. Okay, so if we didn't do that, the mixture would become richer and richer and richer as we go up in the atmosphere. And then eventually, if it gets too rich, you can have a rough running engine. You're losing power because it doesn't have the correct fuel air ratio. You can build up fouling of the spark plugs and so forth. Okay, so we're using this mixture control inside this carburetor to create the correct fuel air ratio. Now, question is, how do you know if you have the correct fuel air ratio, right? EGTs are not a bad way to, if you've got an engine monitor, basically you're going to go, if you're 3,000 feet or less, you're going to be full rich on takeoff. Note your EGTs, right after takeoff. And then as you climb up, your exhaust gas temperatures are going to get lower because it's a richer mixture as you climb, which means that the combustion process is not as hot. So that air coming out of the exhaust valve is not quite as hot. So you're going to have a richer and richer mixture, which means your exhaust gas temperatures are going to get lower and lower. So kind of the easiest way to do it is note your exhaust gas temperature. Whichever one is your hottest, just go by the hottest EGT, whether it's 1400 or 1350 or whatever it is for your engine, and literally just keep that all the way up. All right. So as you climb, let's just say it's 1400 at takeoff. As you climb, it'll go down to 1380, 1370, 1360. Just start leaning it back to bring that EGT back to 1400. Okay, so if you have an EGT gauge, that's the best way to do it. Just note your EGTs on takeoff, lean it till you get up to cruise altitude wherever you are, and just keep that same EGT all the way by leaning it as you go up higher. Pretty simple way to do it, right? Now, what if you have an engine that you don't have that? All right, the best way to get the correct fuel air ratio is you would actually lean it until you started starving it for fuel. So you would lean it until you get a drop in RPM, and then you would increase the mixture, until you had a nice smooth running engine. Okay, so and what we're talking about here is operating in best power, right? So I'm not going to really get into rich a peak and lean a P. We could do a whole video on that, and I probably will one day. But we're talking flying rich of peak in this scenario, keeping the same EGT on takeoff all the way up, leaning it until you get a drop in RPM, then going in, a couple of turns to a nice smooth running engine. But that's what you're doing in this carburetor with the mixture control, is creating the fuel air ratio. Okay, and the throttle is just simply determining how much of that fuel air ratio you're sending to the engine, thus determining how much power you're making in that engine. So the throttle really has no control over the mixture whatsoever, but it's just simply the butterfly valve. So let's look at that just a little bit. Let's look at this carburetor. Make sure I'm going. Yep, here we go. So this is a diagram of carburetor icing, which we will talk about in depth a little bit more. But I just wanted to show you here where that mixture control is. So where are you when you're doing that mixture? What exactly are you doing here? Okay, so here is your mixture control right there. So you can see this little float right over there in that little needle valve. All right, so that is, let me zoom it out just a little bit. That mixture control, that is where you're controlling the fuel air ratio that gets sucked up right into here. So this is fuel that is being controlled by that needle valve over there in the float, and then it's being sucked up here in the venturi into the incoming air. So it's normally aspirated, so this air is not increased pressure or anything. It's just the air that is breathing outside, and then it's mixed with the amount of fuel that you're using there. Okay, so that is the redundancy of the fuel. Remember, 3 things that makes the engine run is fuel, fire, and air. So it's a gravity-fed system. Venting provides a redundancy. Here's the components. So you got, what do you have access into the cockpit to control fuel? All right. So you have the fuel selector. Okay, right here you have access to in the cockpit. You have the mixture control, and then right behind my head here, you have the primer. Okay, so those are the 3 things that you have control of inside the cockpit. We talked about this. The mixture controls the fuel-air ratio. As altitude increases, air density decreases. As the air density decreases, we must lean the mixture or reduce fuel to keep the correct fuel-air ratio. Okay, gasculator helps filter and catch those contaminants. That's what the fuel strainer is. And water's the lowest point in the fuel system. The tanks are vented via the fuel expansion vent tube that we talked about. That's the primary way to vent it, and then vented fuel caps is the secondary way to vent it. So 38 gallons. What do you have access in the cockpit to control the fuel? Is fuel selector, mixture, and primer. Okay. So now, what's the second thing that we use to run that engine? Is fire. Okay, so we talked about fuel. So fuel, fire, and air is what makes that engine run. Fuel, the redundancy there we talked about. And then second is the fire. So what's the fire? So the fire is the dual ignition system. Okay, so our redundancy in the dual ignition, dual meaning 2, right, is the, we have 2 magnetos. Okay, so these magnetos are what we call self-exciting. Okay, so we have 2 spark plugs per cylinder. So one mag controls the spark plug to one of the spark plugs in the cylinder. The other mag would then control the other spark plug in the cylinder. Okay, so what that does is create redundancy, right? So if you lose one mag, so this is kind of like a distributor on a car, basically, except it just does not need electrical power to run. All right, um, but if you lose one mag, that doesn't mean you lose the entire engine. Okay, because you're just only going to lose one spark plug. You have the other mag to still run the other spark plug. So you're going to have a little reduction in power and reduction in efficiency of that engine, because the dual ignition system gives you better efficiency and better power and a smoother combustion process, but you're not going to lose the engine. So your redundancy with the fire is the dual mags. Now, in our 172 mic model, November 61651, one of our mags is electric. So the electric mag is a lot more fuel efficient. However, the FAA will not allow both mags to be electric unless you have a battery backup. And so right now we don't have that in ours, but the left mag in our 172 mic model 61651 is an electronic Surefly mag, and then the right mag is just your standard magneto. So in our airplane, if we lost electrical power, if we turned the master switch off, we would lose this left mag, but we would still have the right mag providing that redundancy. So it's a little bit bigger deal when we lose an alternator or something in flight in our airplane because of that. Your standard setup in most airplanes, again, look at your POH, read the placards on your airplane to determine what you have. But most airplanes, your mags are your just standard Bendix mag, so they do not require electrical power to operate. Okay, here is the switch where we control it. So this is what we have access to in the airplane. So you've got off, you've got right, left, both, and start. So you're always going to be flying it in both, but prior to takeoff, we're checking our redundancy. So we go to the right mag, which shuts off the left mag, and we're running the engine on the right mag. We want, no more than 150 RPM drop or more than a 50 RPM differential between the two. So we're independently verifying before we take off that both mags are working, all right? And then we go back to both. We should get that rise. We go back to the left mag, and then we're operating on the left. We've turned the right mag off, so we're making sure the engine runs just fine, no more 100 or 150 RPM drop, 50 RPM differential between the two mags, just making sure that that works fine, and then we go back to both, okay? So there's our redundancy in the fire, pretty simple. 2 spark plugs per cylinder, so we have 4 cylinders, meaning we have a total of 8 spark plugs. One mag controls one spark plug in the cylinder, the other mag controls the other spark plug in the cylinder. So let's look at this real quick. One mag controls one spark plug in each cylinder. Magnetos use magnets that continuously provide spark without the need for outside source of electrical power. Does not require battery power. We did talk though on R172 mic, the left mag is an electronic mag, so it does, but the right mag does not. Self-exciting, meaning that it doesn't have to have electrical power to operate unless you have an electronic mag, right? The electronic mags are approved through an SEC that require battery power. If both mags are electronic, a battery backup is required. We don't have that. I've looked into it. It's fairly expensive, but it is something possibly might go to in the future. But as of now, it's just the left mag is the electronic mag. And the only way you can stop these mags, because they're self-exciting, is by turning the ignition switch to off. And again, that's on a standard mag. If you turn battery power off to our left mag, because it's electronic mag, it will shut the power off to it. But that's not the case for the right mag. So that's really important. That's the reason why there's an AD on this Bendix switch, that every 100 hours, you as the pilot or the mechanic, whoever's signing off on the AD, you have to shut the airplane off by going to off. So you have to turn the mag to off and make sure the engine quits. What does it mean if you go to off and the engine doesn't quit? That means that these mags are not grounded properly, which is an extremely dangerous situation to personnel around the prop on the ground, because it's hot, if you will, meaning that if somebody was to, move the prop, that it could fire and of course, kill somebody. So that's why that AD is on that switch every 100 hours. You got to go to off to make sure that the mags are grounded properly there. So what makes the engine run? Fuel, fire, and air, okay? So fuel, we talked about the redundancy there in the fuel vent. Fire, the redundancy is the dual ignition system, so 2 spark plugs per cylinder. We got 2 mags, magnetos, to control that. And then last is air, okay? So what is the air? The air is the carburetor. So that is what our air is. So what in the world is our alternate air source in if it's the carburetor? This is going to show you exactly what it is. Carburetor heat is our alternate air. So carburetor heat. Why do we need carburetor heat? All right. So one downfall of the carburetor, and you kind of saw it in this example right here, is carburetor icing. So what happens right here is, again, there is your mixture control, your little needle valve right there. That's controlling the fuel-air ratio. This is your air. You have no control of the air, right? It's normally aspirated, but you do have control of how much fuel you're mixing into here, right? What happens, this little Venturi, it acts like an air full. So Mr. Bernoulli, right? Mr. Bernoulli's principle here. You speed up the air, then you drop the pressure, all right? So that creates a suction. Here's your throttle control. So this is your butterfly valve right here. So that's what you're controlling with the throttle. So this would be kind of like wide open throttle here. If it goes to idle, the butterfly valve is more like that. So that's just controlling how much fuel-air ratio you're sending to the engine itself. But what happens right here, the problem with Bernoulli's principle is when you drop the pressure, then you also drop the temperature, okay? So you can drop the temperature, 30 to 40 degrees Fahrenheit less than what is outside. So if you do that, you drop the temperature, let's just say it's 60 degrees outside, you could well drop the temperature below freezing in this carburetor. So if you combine that with moisture, so what is moisture, right? Relative humidity. So if you have high humidity, which is the moisture content in the air, if you combine that pressure drop with moisture, then you get ice, right? And so how we have to have a way to prevent that, because if we build up ice right here, then that will restrict, you see how it's restricting the fuel airflow to the engine. So again, we don't have to be rocket scientists, but we need to understand the system. So what would be an indication that we're getting carburetor ice? That indication would be an unexplained drop in RPM. So let's just say you're flying the airplane and your RPMs start to drop. Well, what are you going to do? Well, you probably think, oh, my friction, got loose or something with the throttle. So you go and you push it in to no avail, right? It's not increasing the power. But what's happening is it's the same thing as if we were closing this butterfly and like closing the throttle, is we're restricting the fuel air ratio to the engine. So it's getting less and less power. So that's where we would then pull carburetor heat to melt this ice. But again, we may not know that's the issue, right? Anything with that engine, the only thing we have control of is fuel, fire, and air, right? So it's got to be one of those three things. So what do I have access to for fuel? Well, I have a fuel selector, I have a mixture, and I have a primer. Okay, so I'm going to check. Okay, I'm making sure I'm getting fuel, enriching the mixture if it's maybe too lean or something like that. Fire. What do I have control of for fire? I have the ignition source, right? Left, right, both. To see if it's maybe a bad magneto. What do I have control of for air? I can pull the carburetor heat, okay? That is an alternate air source. So now that I've kind of explained carburetor icing, also on this chart right here is kind of a probability chart. The way you kind of use this is here's your temperature dew point spread. So as we know in weather information, as temperature and dew point get closer together, then you have more relative humidity. That's where the clouds are going to be, possibly some visible moisture. So like if you had a temperature dew point spread of 5 and the temperature was, let's see, this is 15 degrees Celsius right here, then you have a high probability of carburetor icing, okay? So keep that in mind, right? But how we prevent that carburetor icing is carburetor heat. So let me show you how that is redundant though. So I told you our redundancy with the air is carburetor heat. Here is why. So let's look at this carburetor air box here. Let's zoom in on it a little bit. Okay, so this is our carburetor right here, all right? This is our air box right here, okay? Now, where air comes into, if you can see right here, it says air intake and filter, okay? So that is on the front of the engine, or on the front of the airplane. So it's right below the prop. That's what we're looking at. There's a filter right there on the pre-flight. We're making sure that that's clear of any obstructions, okay? So air comes through that filter this direction, okay? So that's the normal way we're getting air into this engine, all right? Now, what happens if that air was to become blocked? So let's just say a bird hits it or we hit a balloon and it sucks right to that air intake on the front of the engine. So that means you've cut off the air coming into this air box, right? So if you lose any of the fuel, fire, air, your engine is going to quit. So in that standpoint, your engine is going to quit. But is there an alternate way to get air into this carburetor? Yes, and the way we do that is right here. So this is carburetor heat. So if you'll look, carburetor heat, you see this little lever right there. So what happens, like right now, there is a, with carburetor heat off, there's a little flap in here that kind of looks like that. So that means air coming through the filter, hits that flap, goes up into the carburetor, all right? Now, if that was to get blocked, all right, if we pull the carburetor heat knob, what we're doing is we're moving that flap like this. And what that does is that shuts off the filtered air coming into the carburetor, and it brings this heated, unfiltered air into the carburetor. So we're going to use that, right, to prevent carburetor icing. Read your POH, your AFM, and let it tell you when you're supposed to use carburetor heat. For the 172 mic, it says apply full carburetor heat before closing the throttle. I basically do it below 2,000 RPMs. I mean, it doesn't hurt if you're at a lower power setting. As long as you're not in a climb it's going to hurt your power. Reason why is because you're putting hot air into here. So hot air is thinner air. So it's less pressure, it's thinner air, so the performance goes down when we put heat in. So we don't want that for takeoff or climb, but for the descent, who cares, right? It's a prevention method. But the book says apply full carburetor heat before you close the throttle. So when we apply carburetor heat, again, we're moving a little flap valve like that. That shuts off filtered air coming in, brings in heated air from here. If you notice, there is no filter right here, right? And then if you notice over here in the top right, can't get it a little bit closer there. All right, this is where we're getting that heated air. So this is your, what we call the exhaust shroud. Up here in the top right, you can see the exhaust coming out. Basically, it's a very, very simple system. We pump outside cold air around this pipe that is nearly 1,400 degrees, and we route that through the shroud, and that heats up the air. And then what we do is we use that heated air and we pump it to the backside of this carburetor, and we use that heated air for carburetor heat. But it also serves as an alternate air source. So there's your redundancy in air. So fuel, fire, and air. What we have redundancy for air is the carburetor heat, because when we pull that carburetor heat, we're bringing in an air source from a different direction, so that if this air source became blocked in the front, then we still can get air to that engine, albeit it'll be heated air, but in less performance, but who cares, right? The engine will still run with that air. But again, there's no filter right here, right? So it is unfiltered air when you're using carburetor heat, so keep that in mind. But that's your redundancy with the air. So again, what makes the engine run? Fuel, fire, and air. Fuel redundancy is the vent. Fire is the dual ignition, the dual mags, and then air is the carburetor heat. Okay, so that is what our redundancy is there. So carburetor is susceptible to carb ice, exhaust heater shroud used for heating the carburetor and for cabin heat. So like if you actually see this line right here, that is pumping your hot air for your environmental control. So when you pull the heat knob in the cabin, it's taking the same heat that the carburetor is using, the same exact heat, and it's pumping it into the cabin. Now, one issue with that is if you get a crack in that exhaust pipe where that shroud is, that's a problem, right? You can get carbon monoxide being pumped not only through the carburetor air box, which it doesn't matter, the engine wouldn't be effective with that, but what would matter would be you'd be pumping it into the cabin. So if you get any of those symptoms, dizziness, lightheaded, or whatever, and you're using heat, shut the heat off, ventilate the cabins there to prevent that. But again, carburetor heat is how we prevent carburetor icing. Icing indication would be an unexplained drop in RPM, like we talked about. But it's also a redundancy built into what makes the engine run. Okay, so that was quite a bit, right? But that pretty much finishes up the power plant. It also talks a little bit about the other systems. But what makes the engine run? Fuel, fire, and air. We have 8 spark plugs, 2 spark plugs per cylinder. All right, that is the fire. 2 magnetos to provide redundancy and increased efficiency. The carburetor is the air. Carburetor icing in high humidity, 20 to 70 degrees. And the indication of this is a drop in RPM. So that finishes up our power plant, okay? Prop down here, we have a fixed pitch climb prop. I think I said that in the pilot qualifications. We were talking about controllable pitch prop and complex endorsements and whatever, but we have a fixed pitch climb prop, so we have no ability to change that blade angle of the prop. Now, what I kind of like to do here is I'm going to go to full screen on my iPad. I have terrible handwriting here, but here's our engine, and we talked about it's a Lycoming 0320 E2D, 160 horsepower, 2700 RPM for 5 minutes, 2650 RPM, 150 horsepower, max continuous, no time limit. What makes that engine run, everybody? Fuel, fire, and air. You'll hear that over and 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 over in training. Redundancy, we have redundancy built into all of those, right? Because we only have one engine. So we need two ways to always have fuel, fire, and air to it, right? Fuel redundancy, again, I know I'm saying it over and over, but it's going to, melt in your head, basically. Fuel redundancy is we don't need a redundancy really for gravity, but for the flow. So we have a fuel expansion vent tube for a primary vent. We have vented filler caps for a secondary vent. Fire, we have 2 spark plugs per cylinder, so we have a total of 8 spark plugs. We have 1 magneto that controls the spark to each cylinder. So we have a dual ignition, so we have 2 magnetos and 2 spark plugs. So if you lose 1 mag, you don't lose the whole entire engine. You lose one of the spark plugs, the engine will keep running. And then air, how we get an alternate air, our primary air source is through the front of the carburetor air box, and that is on the front of the engine, just below or on the front of the airplane, just below the prop. And it has a filter there, so we're checking that on pre-flight. If that was to get blocked, then the way we can get air to the engine, another way, is by pulling carburetor heat. And then we talked about what carburetor heat has in the function. Basically, below 2,000 RPMs, we pull it. But again, look at your AFM, and it will tell you when to do that. But attached to this engine is other stuff too. All right. So also attached to this engine would be an alternator. So this is our electrical system. Okay. So this alternator is a 14-volt alternator, and it provides a charge to a 12-volt battery. Okay. Now, 60 amp alternator, 14 volts, provides the charge to the 12-volt battery. This is kind of like water. So you got the higher voltage here flowing to the lower voltage here, meaning it's going to keep this battery charged. Now, when we talk about systems, equipment, and malfunctions, okay, what would happen if we lost the alternator right there, okay? What's going to happen? Do we lose all electrical power? No, you just lose the charging source. So it's kind of like this iPad. You can see this iPad right here. When you have it plugged up into the wall, that's plugged up to the alternator. So it's getting a charge, right? If you unplug it from the wall, then you have taken it away from its charging source. So that's the same thing that's happened here is I've just unplugged the battery from the wall, if you will, okay? So does this iPad go dead when I unplug it? Of course not, right? But now, let's just say in the iPad standpoint, if I wanted to use it for 3 days and I don't have the ability to charge it, am I going to sit there and watch YouTube videos at full bright? Like, no, you're going to start like powering things down, right? And conserving energy. You would do the same thing here with the battery. Battery, depending upon, how old the battery is and capacity, you're going to get anywhere from 30 minutes to an hour out of it. But it's also dependent upon how many amps you're pulling off of it. So that's where you would turn off anything non-essential. So, turn lights off, turn, every radio off except one, so forth, right? Unplug your cigarette lighter, chargers, and whatever, right? You're just going to conserve that battery. But really, really really simple electrical system here. Let me go, there it is right there. So here's our alternator that's providing the charge to our battery. This alternator is literally just a belt. We're checking the tightness of this belt right there. But so the engine turns that alternator, provides the power. We've got 14 volt, provides charge to the entire electrical system. We only have one alternator, so there's no redundancy, and it charges that 12 volt battery. But again, when you lose your alternator, it doesn't mean that you lose all electrical power, right? You're just unplugging it, so you still have your battery there. So electrical system here is you got a 12 volt battery. You have your 60 amp 14 volt alternator like we talked about that provides the battery charge. Now we have circuit breakers that protect the system. All right. So if a circuit breaker pops, it's likely doing its job, right? So we're only going to reset a pop circuit breaker once if it's absolutely necessary for safe flight. All right. That would greatly depend upon, I only have one alternator. I don't have redundancy there. So if I'm flying at night or in, IMC, instrument meteorological conditions, and my alternator goes out, okay, or the circuit breaker pops, okay, I'll probably try to reset that because that's fairly important, okay? And especially in R172 because we have an electronic mag. So now losing electrical power would mean that we're losing a redundancy to the fuel, fire, and air, right? And if we ever lose that redundancy to fuel, fire, and air, I'm getting the airplane on the ground, okay? I'm declaring an emergency. If I lose a mag, if I lose, any of my redundancy, okay? Anything with the fuel, my fuel selector handle breaks off or whatever, I'm declaring an emergency, getting it on the ground, okay? I'm not messing with fuel, fire, and air because I only have one engine, right? So kind of the same thing here. We only have one alternator. So, but if it's a severe clear, day VFR, I don't know. I probably would not reset that. It's probably popped for a reason, okay? But you do have the prerogative as PIC to make that decision, but we're only going to reset that once. If it pops again, if you decide, okay, I need this alternator, I push it back in. If it pops again, you're done, okay? Do not reset it a second time. You could cause an electrical fire, okay? And if you do get an electrical fire, you just got to shut the master switch off, right? Just shut off every bit of electrical power to that airplane. Now, in our airplane, that means you're going to lose a mag like that. But if you have a conventional airplane with conventional mags, you lose absolutely nothing with the engine. Okay. Here's your electrical component. So the flaps are electrical. Here is one of your six packs. Your turn coordinator is electrical. We'll talk about that in just a minute. Your radios, your GPS, your transponder is electrical, and your fuel gauges are electrical. Also, with our airplane, we have an engine monitor in there that is gives us oil pressure, it gives us oil temperature, it gives us the cylinder head temperatures, exhaust gas temperatures, it gives us fuel flow, temperature, percentage power. It gives us absolutely everything. Now, of course, it is electronic. All right, so if we turn our battery power off or whatever, we're going to lose our fuel gauges, we're going to lose our oil pressure, we're going to lose our oil temperature indications, and so forth. Okay, so a little bit bigger deal when we're talking about the electrical system there. So pretty simple electrical system, right? So you've just got that and one alternator charging that 12 volt battery. Okay. Another thing that is attached to this engine is a vacuum pump. Okay. And what does it provide power to? All right. That is where we start getting into our repeated static system, which is what we're going to do in the second video. Okay, we went about an hour here, so I think that's enough here. We're going to get into the rest of the systems, which won't take quite as long, but on the next video. But I just want to kind of show you everything that's connected to the engine. We only have one engine. Our redundancy is built in the fuel, fire, and air that we talked about. We have a vacuum pump that's attached to that engine, which we'll talk about in the next video. and then our alternator is our electrical system. Thanks for hanging in there. I know these are long videos, but this is pretty much everything you need to know operation systems wise. Appreciate your commitment to continuing education. I did want to show you, though, the type certificate data sheet. Actually, I tell you what, it's actually on the website. So let's go to aircraft documents. Here's a 172 type certificate data sheet. There it is right there. So can't see that. There we go. So this is on the documents section of the website. But if you can see the type certificate data sheet, man, please look up the FAA type certificate data sheet for your aircraft. You can do it on the FAA website. I went through that in the airworthiness requirements of how to do that. So if you don't know how to do that, go look at the airworthiness requirements video and scroll past to get to the type certificate data sheet. But this tells you what engine you have, fuel, your engine limits. Now again, for our 172, this is not what we go by because we have an STC for a different engine, right? And I showed you that in the beginning of the video. But it also is going to come in here and tell you your fuel capacity right there. There's our 42 gallons, 38 gallons usable, oil capacity, maximum baggage. This will all come into play in performance and limitations and stuff. But the type certificate data sheet is a treasure trove of information, so please look that up. So anyways, appreciate you watching this video of Operation Systems Part 1. We'll get into the Operation Systems Part 2, where we're going to talk about the vacuum pump, the pedostatic instruments. We're going to talk about primary, secondary flight controls, oxygen systems, and a lot more fun stuff. So thanks for watching.